Okay, welcome back. 1 second. Sorry. Okay, so this is now chapter 9, and we're getting into probability, so we're kind of done with having to worry about proofs for a little bit until we get back into graph theory, and then we'll worry about it again. Okay, but for now, I'm just counting things and the probability of events. Okay, so the probability of something happening. Okay, so an example, let's just start with an example here. Problem 2, we're uh, tossing a coin twice. Okay, what is the events that could take place here? And this is called the sample space. So the list of all possible outcomes is the sample space. Okay, and we're talking about flipping a coin twice. Obviously, there's only one L in flipping. Okay, so we'll use H for heads, T for tails, and heads, tail, HT would be heads on the first flip, tails on the second. Okay, so all the possible ways this could happen: you could get heads, heads, you could get heads, then tails, you can get tails, then heads, and then you get tails, tails. Okay, okay. Let's say I want to know the probability of getting at least one head. So we can write that the probability that we get at least one head. Okay. Okay, in order to figure out probability, you basically take a ratio of two things. You take the number of things in what's called this event space, which is getting at least one head, and then you divide it by the number of things in the sample space. Okay, so this pound symbol means number, right? So number of things in the event space over a number of things in the sample. Okay, so what is the set? What is the event space, right? Getting at least one head. You can go back to the original set at the top here, S, and look for elements that have at least one head. So this guy, and then this guy. So at least means one or more, right? So the elements in this first and this event space set, HT, and we're looking for the number of things in here, TH, and then TT. Okay, we know the number of things in the sample space. There's 1, 2, 3, 4 things there, so we'll put 4 down here. And then the number of things in the event space, well, there's 1, 2, 3 things there, all over 4, and that turns out to be the probability. Okay, so the probability of an event, E, okay, which we'll label as P of E, is just going to be the number of things in the event space divided by the number of things in the sample space. Okay. And some books use big N for the pound instead of this pound symbol, so they may write N of E divided by N of S. Maybe our book does that. I don't remember. Okay. But that's the idea, and we're presuming that all of these events are kind of have the same probability, so we're not dealing with a coin that's kind of weighted, or maybe a coin that has two heads on it. None of that business. Okay, let's maybe look at maybe one or two more of these. So the probability that a coin, that the first coin is a heads. So okay. So thinking about that, what are the events in that event space? So that's heads, tails. You can have heads, heads. There's only two things there. Okay, all over 4. So this is 2 over 4, which is 1/2, 50% chance. Okay. What about the probability that A and B are both heads or both tails? So the first and then second flip, both heads or both tails. That'll be 1/2 again, right? Because the things in that event space are heads, heads, and tails, tails. There's only 2 of them out of the 4. So again, that's 2/4, which is 50% chance. Okay. Okay, let's take it up a notch and think about flipping 3 coins. Okay. So part A, they want you to write out the sample space. And we'll work more with probability multiplication principle later, but basically if you have 2 possibilities for each event, and you have 3 events that are not dependent on each other, to figure out the number of things that could possibly happen, you just multiply the number 2 times 2, in this case 2 times 2 times 2. That'll tell you how many things are in S. So in this case, the number of things in S should be 8. Okay, let's list them. So there is head, 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 tail, head, tail, head, tail, head, head. This could get kind of tedious, but tail, tail, head, tail, head, tail, tail, whoops, head, tail, tail, and then tail, tail, tail. And count them up, make sure you get 8. So 1, 2, 3, 4, 5, 6, 7. Yeah, got them all. Okay. Okay. What's the probability that 1 toss out of the 3, so exactly 1 toss is a head? Okay, so you just go back through and find them, right? So the ones where 1 is ahead. So this one, and this one. There's 3 of them out of the 8. So 3/8. That's your probability. Let's look at another. Whoops. I guess that was part I, part B. Part double I. The probability at least 2 tosses are heads. So this means the things that where you have 2 heads, and also the things where you have more than 2 heads. So this is 3 heads, that'll work. It's 2 heads, 2 heads, 2 heads, and that's it. So there's 4 of them out of the 8. So you have a 1/2 or 50% chance of that happening. What's the probability of not getting any heads? This is, you can think of this in terms of complements. It'll be 1 minus the probability of getting at least 1 head, right? So it should be 1/2, or sorry, it should be not exactly 1/2. It'd be, so how many times do I want to think of it in terms of the complement? So the probability of no heads is 1 minus the probability of getting at least 1 head. Okay. We could count up the probability of getting no heads, right? We can go through and just literally circle those. So there's only one where you get no heads, and that's right here in the sample space that I circled in red. So it should be 1 out of 8, right? But you could also say it's 1 minus the probability of getting at least 1 head. So let me go through and circle the 1 head cases in green, right? So at least 1 head. So this one has at least 1 head. This one has at least 1 head. This one, this one, this one, this one, this one. The only one that doesn't have 1 head is that one. Okay. So there's the probability of getting at least 1 head is 7/8, and if you subtract those, you get 1/8 again. Okay. Okay. So that'll come up. Sometimes it's easier to figure out this probability, or maybe easier to figure out this probability. Okay, and you can kind of work with those interchangeably. Something so it's kind of a simple little deal, counting the number of elements in a list. Okay, so how many numbers are there from 3 to 9, including 3 and 9? So we'll say from 3 to 9 inclusive. So you can literally count them, right? You hope for a formula though. Let's count it. So 3, 4, 5, 6, 7, 8, 9. So there's 1, 2, 3, 4, 5, 6, 7 things there. Okay. Example. How many? Same kind of question. How many numbers from 211 to 1,235, right? That's a little harder. We can't count that out, so we want a formula. Okay, can I just subtract those two numbers? Can I subtract this guy and get the answer? Well, let's look back at the other problem, right? Can I subtract 9 and 3 and I get 7? 9 minus 3 is 6. No, that does not work. Okay, it's actually what you're going to have to do is go the big number minus the small number and then add 1. So you're actually going to have to go 1, 2, 3, 5 minus 2, 1, 1 and then add in 1. Okay, and that'll give you the number of numbers from 211 to 1, 2, 3, 5 inclusive, including the endpoints there. Okay, so 1, 2, 3, 5 minus 2, 11. So 4, 2, 0, 1, and then plus 1 will be 1,025 numbers. Okay, so that formula will get you through some hard times. In other words, if m and n are integers and n is the big number, so m is less than or equal to n, then there are n minus m plus 1 integers from m to n inclusive. Okay, so that's helpful. Let's take it up a notch. Okay, so let's look at number 22. How many 3-digit numbers are multiples of 6? Okay, so this is a different kind of problem, but we're going to use that n minus m plus 1 idea inside of it. Okay, so 3-digit numbers. What's the first 3-digit number? Well, that's 100. Okay, and then we have 101, and then we have 102, and then 103, 104, right? 105. There's a method to my madness, don't worry. 106, 107, 108, dot, dot, dot. 996 is in there somewhere, dot, 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 all the way up. What's the last 3-digit number? Well, 999, right? Okay. So what I want to do is kind of figure out which ones are multiples of 6, right? So I do some division with my calculator. Divide 100 by 6, that doesn't work. Divide 101 by 6, that doesn't work. 102 is divisible by 6. In fact, you can write it as 6 times 17. Okay, and then it's just a matter of adding in 6. So the next one that's divisible by 6 is 108. 6 times 18. And then at the end, the biggest number that's less than 999. So I kind of take 999, divide it by 6, take 998, divide it by 6 backwards. Or you could divide 999 by 6 and then take the floor of that number, and that's going to be the biggest one. But anyways, you could find it 996 is really 6 times 166. Okay, so how many of these guys are there? Well, the first one is 17 and then 18. So there's 17, then 18, then 19, and then that goes all the way up to 166. So we need to count those. We need to say this is 1, 2, 3, all the way up to what? Right? And how do we count those? Well, we just go, it's the n minus m plus 1 formula. Right? So in our case, it's 166 minus 17 plus 1. Right? Which in this case is 150. So 150 numbers, 150 three-digit numbers are divisible by 6. Okay, so part B, what's the probability then that a three-digit positive integer is a multiple of 6? Well, we already know then the event space is 150. We just need to figure out the sample space. So how many numbers are from 100 to 999 inclusive? Okay, so we got 999 minus 100 plus 1. And of course, that's just going to be 900, right? So that's the number of elements in our sample space, and then you could reduce it. The website may ask for decimal, usually a percent, so 16.7% possible chance. They use things like this to see if people are cheating on their taxes. Like they know if they use they sort of know how the number should be distributed, and they can go through and look and see if you're using a certain number too much or too little, that you probably have cheated on your taxes, because they know what's the probability of seeing these numbers, right? So that's interesting. But anyways, probability of a three-digit positive number is a multiple of 7. So same kind of question, it's just now instead of multiple of 6, multiple of 7. Okay, so the denominator is 900. We just need to figure out the multiples of 7. Okay, so 100, try to figure out if that's divisible by 7. No, and it turns out you have to go up to 105 to find the first one that's divisible by 7. And then if you divide 999 by 7, you'll get 142 point something. So 142 times 7 is the biggest one, and that's 994. Okay. So this one is 7 times 142, and then this guy is 7 times 15. Okay, so the number of numbers in there that are divisible by 7, you just take 142 minus 15 and then add 1, and you get 128. Okay, so the event space is 128. It's approximately to the nearest tenth of a percent, 14.2% probability. Okay, and you'd kind of expect that because there's not as many multiples of 7 will fit in that range. There's less of them. Okay, so you expect that probability to be a little less than the probability of 6, of a number being divisible by 6. There's other problems. They kind of play around with this idea. Like puzzle questions, like the largest of 56 integers is 279. What then is the smallest? Okay, and you use the formula to figure it out. So the largest one is, from the formula n minus m plus 1. The largest one is 56. Then we subtract away m plus 1, and we know there are Oops, sorry. This is the n value is the 279. Okay. The largest one is 279, and you know there's 56 of them, so that n minus n plus 1 should equal 256. And then to find the smallest number, you just solve that equation for m. Okay, so m ends up equaling 280 minus 56, which of course is 224. Okay, let's maybe look at some of the problems in the software. We have a little time. Okay, so kind of scrolling around. All right, so there's some of these weird array problems. Let's look at this one first. No. Let's look at this one. Okay, two faces of a six-sided die are painted red, two are painted blue, and two are painted yellow. The die is rolled 3 times, and the colors that appear face up on the first, second, and third rolls are recorded. Find the number of elements in the sample space whose outcomes are all possible sequences of 3 rolls of the die. Okay, in this case, you can kind of just pretend it was a 3-sided die. Is that geometrically possible in our reality? I don't think so. But you can pretend you have a 3-sided die, and it's a 3-sided die. Oh yeah, you can't you? It's a cylinder, right? A cylinder is kind of a 3-sided die. Okay, so anyways, once we've established that, we can roll the thing, and so what are the possible outcomes in our sample space if we have these 3 colors? Okay, so let me go back to my notes here. Scroll down. So we have, what are the colors? Red, blue, and yellow. So our sample space, if we're rolling 3 rolls in a row, so red, red, red. So there's red, blue, yellow. Oh, this is going to be brutal, right? Because in each roll you have 3 possibilities: red, blue, or yellow. Okay. Each roll is independent of the previous roll, and there are 3 ways to do each roll. So therefore, there's going to be 27 items in your sample space. And you can sit there and list them out. Okay. So red, 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 red. Now the ones with the blue. Okay. And then red, red with yellow. And then 1 red versions. So you'll have reds with blue, blue. You'll have reds with blue, yellow. Okay, etc. There's a ton of them, but there turns out to be 27. Okay, and you literally go through and list them if you want. I'm not going to. Okay, part B, find the probability that exactly one of the colors that appears face up is red. Okay, so I just need to kind of figure out that event space. At least 1 red. So red, 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 blue, red, red, yellow. And then of course we have red, blue, red, and then blue, red, red, and then we have red, yellow, red, and then we have yellow, red, red, at least 1 red, and then we have the ones with just red, right? So red, blue, blue, and then blue, red, blue, and then blue, blue, red, and then we have red, yellow, yellows. So red, yellow, 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 red, yellow, and then yellow, yellow, red, and then we have red with mix of blue and yellow. So red, blue, yellow, red, yellow, blue, and then we have red, and all the variations of those, right? Okay. Am I doing what they want? Find the probability of the event that exactly one of the colors that appears face up is Oh, exactly one. Sorry, I'm doing a lot harder of a problem. So exactly one is not a big issue. Sorry about that. Exactly one color is red, blue, yellow, or red, yellow, blue, or the other versions of those, right? So blue, red, yellow, um, blue, red, yellow, and then blue, yellow, red, or yellow, red, blue, and then yellow, blue, red. Was that all of them? Did I get all of them? So exactly one. No, we need the red, yellow, yellows, and all their versions. Yellow, red, yellow, 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 red, and then we need the red, blue, blue, and the blue, red, blue, 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 red. 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 27. So the probability of that particular event of getting exactly one red is 9 over 27, which is 1 out of 3. Oops, I must have screwed that up. Oh no! 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sorry, I can't count. 12 over 27. You should learn how to count, people. Okay, it's not cool to not know how to count. Okay, 12 over 27 is divide top and bottom by 3. You get 4 over 9. Sorry. What else do they want? Find the probability of the event that at least one of the colors that appears face up is red. That's what I was originally doing, man. Okay, so it's going to be all of these. That's where one color is red. So there's 12 of those. And then the ones where two colors are red, and that was these guys. Okay. So 12, 13, 14, 15, 16, 17, 18, 19. The one where all three are red. So the probability of at least one red is going to be, what did I just say, 19 over 27? Okay, so 19 over 27, yeah. Okay. Some earn problems. There's one of those multiple of 7 problems. Maybe we should do an earn problem. I don't think I did that. No. Let's do one of these list problems. Okay. So a one-dimensional array is basically just a list of numbers. When you see that A bracket 1, like listed like this, A bracket 2, you can just think of those as A sub 1, A sub 2, and like a sequence. Okay, so you just think of it as A sub 1, A sub 2, A sub 3. Okay, what is the problem asking? So how many elements are in an array? So in this particular case, our array is going from A sub 1 to A sub n. So how many elements are there? So from A sub 1, A sub 2, all the way up to A sub n. So the number of elements will be n minus 1 plus 1, which is n. Okay, so that would be part A. Part B. How many elements are in the following subarray? So they're going from 4 to 39. So basically A sub 4, A sub 5, all the way up to A sub 39. Okay, so again, that'll be 39 minus 4 plus 1, which is going to be 36. Okay, yeah, 36. This one's kind of weird. What's the probability that a randomly chosen array element is in the following subarray? Okay, so we have 3, 4, all the way up to m. And then we need the probability that a randomly chosen element is in that sequence. Okay, so part C, our array A3, A4, all the way up to A sub m. So first we need the event space and divide that by the number of things in the sample space. So the number of things in the event space, how many elements basically are there? So that would be m minus 3 plus 1, okay, which is m minus 2. And the number of things in the sample space, well, the sample space is the array A1, A2, all the way up to A sub n. So the number of things in the sample space should be n minus 1 plus 1. Okay, so your probability of E in this case will be m minus 2 all over n. Okay. What's the probability a randomly chosen element is a subarray if n equals 59? Okay. Oh, and then we have some weird floor notation in there. Okay, okay, so part D. N is given, my problem, the red number is 59. Yours may be different. And our subarray is going from A sub n over 2. That's the floor of n over 2. A sub floor of n over 2 plus 1. All the way up to A sub, I think it's n. Let me see. Yeah, A sub n. Okay, this is kind of easy because they tell you it's 59. So 59 divided by 2. Okay, so the 2 goes in there. 4, 1, 9, 8. So, whoops, 9 maybe. 18, 1, 29 point something. So the floor is 29, so it's A sub 29. All the way up to A sub 59. And what are we doing? What's the probability? No. Yeah. What's the probability that any randomly chosen array element is in this subarray if n is equal to 59? Okay. So what is that going to be? It's going to, the event space, there are 59 minus 29 plus 1 things in that. And then the sample space, there's 59 things in there. So 59 minus 29 is 30 plus 1 is 31 all over 59. Yay, we got it. Okay, let's see if there's anything else weird. 28th element. So these are just applying that formula basically. Okay, I think that'll do it for us, and we'll see you next time. Thanks for watching.